All right, so today we are going to start talking about what is effectively our last topic for this class, which is loosely filter design, okay? So the first thing that I want to talk to you guys about is how we can scale things. Okay. So essentially, you may have noticed that in all of our analysis and all of that kind of good stuff for the resonant circuits that we've dealt with in this class, the values of the components have been somewhere around 1, right? So effectively, we can analyze things with element values of like 1 ohm, 1 Henry, or 1 farad to figure out how everything is related to each other. And then we can use what's called scaling in order to adapt it for other frequencies, other component values, and all of that kind of good stuff. And so we're going to talk about how that works today, okay? So the first type of scaling that we're going to deal with is magnitude scaling. So in order for us to discuss magnitude scaling, we need to recall that the impedance of a resistor is simply the resistor value itself. The impedance of an inductor is J omega times the inductor value. And the impedance of a capacitor is 1 over J omega times the capacitor value, okay? So in magnitude scaling, we are going to multiply the impedance of each element by a scaling factor. And we're going to call this scaling factor K sub M, okay? While we hold the frequency constant. And in doing so, this gives us new relationships. So this scaled impedance relationships of, so I'm going to call this first one for a resistor ZR prime, where the prime designation literally just means a scaled version of the impedance of our original resistance. Macaluso, why are you laughing? So this is simply going to be Km times our resistor impedance ZR, or just Km times R. And so essentially our scaled resistor value is just Km times R itself. For an inductance, we'll have ZL prime, our scaled inductor impedance, is Km times ZL. So this is going to give us J omega Km times L. And so our scaled inductance value is Km times L. And then lastly, for our capacitance impedance, we'll have ZC prime is Km times ZC, which is going to look like Km over J omega C. And from this, our scaled capacitance value is C divided by our magnitude scaling factor. So I want us to make a couple of observations here really quickly, okay? So for a series resonant circuit, let's look at what our scaled version of our resonant frequency will be first, okay? So for a series resonant circuit, we know that we should have 1 over LC. And if we scale the inductance and we scale the capacitance, we'll have a scaled version of our resonant frequency that's a square root of 1 over scaled L times scaled C, right? So if I substitute things in here, I'm going to have the square root of, so let's see, so my 1 over L is going to look like a Km times L. My scaled version of C is going to look like a C down here and a Km in the numerator. These guys obviously cancel each other out. And so we're left with simply the square root of 1 over LC or omega naught. So magnitude scaling does not change our resonant frequency at all, okay? If we look at our quality factor, Q, and we want to see how scaling impacts that, I'm going to use the relationship 1 over R prime times root L over C, so that we have the effects of scaling all three components built in here so we can see what impacts it has on Q. So this is going to look like 1 over Km times R. And then I'm going to have the square root. So L is Km times L. C prime is going to be C, and then I'm going to have that over Km. So that's going to put a Km squared up here in the numerator. And hopefully, obviously, the square root of Km squared is Km over Km. Those guys cancel each other out. And we're left with 1 over our original R times the square root of L over C, which is our original quality factor. And then lastly, the scaled version of our bandwidth is omega naught prime over Q prime. And since we just found out that magnitude scaling doesn't change omega naught at all, we can just get rid of the prime. Magnitude scaling doesn't change our quality factor at all, so we can get rid of the prime. And so we see that our bandwidth is not in any way, shape, or form influenced by magnitude scaling either, okay? So technically, we derived all of these for a series resonant circuit, but for a parallel resonant circuit, remember that all of those relationships are effectively the same. Or actually, let me rephrase that. So omega naught is literally the same, but our Q relationship is the inverse. But if we flip that expression over, it's literally not going to change any of those things either. So effectively, it doesn't matter whether we have a series resonant circuit or a parallel resonant circuit. Magnitude scaling is not going to change resonant frequency, bandwidth, or quality factor. Okay. So how we change those particular parameters is frequency scaling. So in frequency scaling, we can scale the frequency by a factor of K sub F. While keeping impedance constant. So our scaled version for our inductance is going to be J times omega KF times L prime, and this has to be equal to the original impedance of J omega L. And so rearranging this guy, we see that our scaled version of inductance is simply our original value divided by our frequency scaling factor of Kf. For our capacitance, our scaled version is going to be 1 over J times omega Kf times C prime. And this has to be the same as 1 over j omega c. And so we can see then that our scaled version of c is just c divided by kf. So I want you guys to notice something here really quickly. When we look at our magnitude scaling for inductance and capacitance, we have the inductance is multiplied by Km and the capacitance is divided by Km. When we look at our frequency scaling, we're both, in both cases, we're dividing by Kf, okay? So just as a quick question, why wouldn't we have a relationship for frequency scaling for resistors? Because they are independent of frequency, right? So we shouldn't have to worry about scaling resistors in the frequency domain. So let's look at what happens then to our resonant frequency quality factor and bandwidth. Once again, just deriving things for a series resonant circuit, but it'll work the same way for parallel resonant circuits. So our scaled version of our resonant frequency is once again going to be 1 over L prime C prime. And so this is going to look like we're going to have an L and a C in our denominator. Since they're both divided by KF, that's just going to put a factor of KF squared in the numerator, which is simply KF times the square root of 1 over LC, or KF times omega naught. So our resonant frequency is going to be shifted by that scaling factor. That's the whole point of frequency scaling. For our quality factor Q, we're going to have 1 over R times the square root of L prime over C prime. So that's going to look like 1 over R times the square root of KF times L over KF times C. Those scaling factors cancel each other out. So this gives us 1 over R times the square root of L over C, which is just our original quality factor. So it looks like neither magnitude nor frequency scaling has any impact on the quality factor of the circuit at all. And then lastly, we have our bandwidth. So the scaled version of our bandwidth, once again, is omega naught prime over Q prime, which is going to be KF times omega naught over Q, which is simply KF times our original bandwidth. Okay. All right, so lastly, let's talk about what happens if we do magnitude and frequency scaling simultaneously, because that's actually more likely to be the case, okay? So our scaled version of our resistance is literally just going to be Km times R. Right? Our scaled version of our inductance, we're just going to combine those effects, right? So our magnitude scaling gave us a factor of Km times L. Our frequency scaling gave us L over KF. So this is just going to look like Km over KF times L. And then lastly, for our capacitance, we are going to have, so we had C over Km for our magnitude scaling and C over KF for our frequency scaling. So when we have both scalings going on for capacitance, it's just C divided by Km times KF. And then lastly, looking at the effects of both going on for resonant frequency, it's just KF times omega naught. It has no impact on our quality factor whatsoever. And our bandwidth, once again, is simply scaled by our frequency scaling factor. So I hit you guys with a bunch of equations and all of that kind of stuff. It's hard to understand what's going on until we put it in context. So that is exactly what I want to do. So let's work an example here. So I have designed, using the filter table that I gave you guys in front of you, what's known as a fourth order Butterworth low pass filter. So I have my input signal in series with a 1 ohm resistance, and I mentioned the table, but I don't expect you guys to be able to use it or anything just yet. I'm just telling you where these numbers came from. I didn't pull them out of my ass.
That may decrease instead of whereas for the.
Yep. Thank you. So this particular system, or filter circuit, like I said, it's a fourth order Butterworth filter, meaning it has 4 different energy storage elements that can't be combined into any simplified energy storage elements. And this circuit was designed to have a cutoff frequency. So let's call that omega C is equal to 1 radian per second, for a matched resistance of RS is equal to RL is 1 ohm. So let me define some things really quickly here, okay? So this is our source resistance, RS. It's typically representative of the internal resistance of our voltage source. So if we had something like a function generator, like we have over in the lab that you guys are working on right now in NEFCON 218, that value would actually be 50 ohms because the terminals of that particular device are rated for 50 ohms of internal resistance, okay? This capacitor right here, we're going to call C1. This is our inductor, L1. Excuse me. This is our capacitance, C2. This is our inductance, L2. And then this resistance right here is our load resistance, okay? All right, so before we figure out scaling and all of that kind of stuff, how this is going to work, I want to show you something on LT Spice. Let's see if I can find a mouse here as well. So let me make this bigger so we can make sure I'm not trying to bamboozle you guys in any way, shape, or form. Is this the circuit that I've drawn, except that I put a value on the voltage source? Okay. So all we're doing here is the AC analysis like we did in circuits 2, because we're looking at effectively how a filter behaves. So for when you guys have to do this for your homeworks, take-home tests, and all of that kind of good stuff, I'm just went into the advanced tab and I put my AC amplitude as 1 volt. I left literally everything else blank because I just want simply a 1 volt input signal across all frequencies so that when I take my output voltage at this node, that divided by 1 is my transfer function for my system. Okay, so I'm simulating this circuit. Nothing particularly wild or crazy there. Let me just make this thing fit. And my output voltage is the voltage drop across that resistor R2, and I have what looks like a low pass filter. Okay. Now, this is a little bit different than the low pass filter that we dealt with in circuits 2, either a first order low pass filter or a second order low pass filter, because we're taking our output voltage across resistance. So what I'm trying to bring to your attention right here is that we don't start off at 0 dB. We actually start off at -6 decibels, and I can show you that pretty easily. If I just take my cursor and move it over here, we see that we have -6.029 blah, blah, blah. That is effectively 20 times the logarithm of 1/2. So my first question to you guys is, why are we starting out at -6 dB? Anybody have any thoughts? So at DC, what would this circuit look like? Our capacitance here would be an open circuit. This inductance here would be a short circuit. This capacitance would be an open circuit. This inductance would be a short circuit. So we have a voltage source connected to 2 resistors in series, and we're taking the voltage drop across the second resistance. This looks like just a simple voltage divider circuit. Our output voltage is going to start off being exactly 1/2 of our input voltage, which is why we're starting at -6 dB as opposed to 0 dB. So our corner frequency or our cutoff frequency should then be at roughly -9 decibels, because it's 3 decibels lower than the maximum value. So if I slide this thing over and I look for where we hit -9 dB or something really close to it, we're at 159.5-ish megahertz. Or excuse me, millihertz, pardon me. I said that this thing was designed for an angular frequency of 1 radian per second. So what's the problem here? Or is there a problem, I guess would be a better way to put it. So radians per second is an angular frequency. This graph is in hertz, which is a linear frequency. What's the relationship between those two things? Omega is equal to 2 pi f, right? So if we want omega of 1 radian per second, what is our frequency? 1/2 pi. Put 1/2 pi in your calculator and tell me what you get. I bet it's 0.159 and some change. Yeah, okay. So this exactly matches what we were expecting, okay? We have a low pass filter whose cutoff frequency or -3 dB frequency occurs at 1 radian per second or 159 millihertz. Just as a quick sanity check type thing here, if I move my cursor here at 1 hertz, we can see that our magnitude is -70 decibels. If I go 1 decade later, so to 10 hertz, we're at -150 decibels. So what's that change? -80 decibels per decade. Does that make sense with a 4th order filter? Absolutely. Every order is an increase of -20 dB per decade, just like we've seen previously in the class. So we have a system effectively where, using our filter tables and stuff like that, we are told how to get a 4-time repeated pole effectively at a particular frequency. Okay. So if we had a 5th order filter, it would be dropping off at -100 dB per decade. If we had a 6th order filter, it would be -120 dB per decade, and so on and so forth. So yeah, if we want it to drop faster, or that if we want to make that slope larger, we increase the order of the filter. Amir. So it really depends, and also those are going to be active filters and not necessarily Butterworth filters as well. So we're going to talk about Butterworth filters, which are used in applications where we don't necessarily want high Q, we want a very flat pass band. We're also going to talk about Chebyshev filters, which give us high Q, but introduce ripple in the passband that we have to talk about. We may have time to talk about Besnell filters as well, but then there's also elliptical. There are tons and tons and tons of different filters that are used for different applications. Some of them give us better performance at lower orders, but there are trade-offs like having ripple in the passband and all of that kind of good stuff. So it's hard to say, oh, for this particular application, you would do this one thing. It depends on what you want for the entirety of the system. Does that make sense? Hojun? So Butterworth filters are used in really anywhere just we want simple passive filtering. So if we are not, so like we could use this in rectifier circuits and things like that, where we just want effectively things smoothed out. This is used in a lot of power supply filtering where we're not worried about, or we intentionally don't want to add noise to our signal and things like that. Just for what it's worth, this is what's known as the Cauer, C-A-U-E-R topology, the Sallen-Key filter topology that I gave you guys for your second design project is a different way to do Butterworth filters as active filters. All right, so just wanted to make sure that this circuit gives us the performance that we are expecting. So we do have a 3 dB cutoff frequency at 1 radian per second or 159 millihertz. So what if we wanted, so we want to design a fourth order Butterworth filter. Excuse me, low pass filter, that's important. With a cutoff frequency FC of 50 kilohertz, where RS is equal to RL is equal to 10 kiloohms. So using literally just these two pieces of information, we should be able to figure out what our scaling coefficient for our magnitude scaling is, Km, and our frequency scaling, Kf, right? So Kf should simply be our corner frequency or resonant frequency after scaling divided by our corner frequency or resonant frequency prior to scaling, okay? So that's going to be 2 pi times 50 kilohertz. So that's 50 times 10 to the 3 hertz all over 1 radian per second. Just for what it's worth, a hertz is a unit of per second. So hertz cancels this per second down here. Radians is effectively a dimensionless quantity. Or another way to think about it is that 2 pi is giving us an angle in radians. So ultimately here, our scaling factor is essentially just pi times a factor of 10 to the 5, and it is a dimensionless quantity. So 2 times 50 is 100, which is 10 to the 2, times 10 to the 3 is 10 to the 5, and then the pi comes out. We all okay with that? Our magnitude scaling coefficient is most easily figured out by looking at our resistance, right? So our resistance after scaling over our resistance prior to scaling gives us our magnitude scaling factor. So this is 10 kiloohms over 1 ohm is a factor of 10 to the 4. And so using these values, we could say that our inductance L1 prime, so our magnitude and frequency scaled value, would be Km over Kf times L. So that's going to look like 10 to the 4 over pi times 10 to the 5 times 1.848 henries gives us 58.824 millihenries. Going to do L2 the same way. Km over Kf times L2. Sorry, I should have put a 1 there. So 10 to the 4 over pi times 10 to the 5 times 0.765 henries gives us a value of 24.351 millihenries. Our scaled version of C1 is going to be C1 over Km Kf. So that's going to look like 0.765 farads divided by pi times 10 to the 9, or 243.507 picofarads. And C2 prime is simply C2 over Km Kf. So that is 1.848 farads over that same factor of pi times 10 to the 9, which gives me 588.237 picofarads. So what I'm going to do now is I'm going to copy this circuit. Let's get this out of the way, close this out just for the hell of it. So Control C. V. All right, so our resistors should now, hold on, we'll get rid of this thing. So this guy is now a 10K, and this guy is now a 10K. This guy right here is, let's see, so that's my C1, so that's 243.507 picofarads. This is the guy that's replacing L1, so this is 58.824 millihenries. This is the guy that's replacing C2, so that's 588.237 picofarads. And this is the guy that's replacing L2, so this is 24.351 millihenries. It's going to give me an error if I don't delete this thing right here. And if I simulate this, so if I look at the output of this one, that's my original thing. And what I should see is effectively the exact same graph, but my cutoff frequency should now be shifted over to the right to 50 kilohertz. So if we look at, was it 50 kilohertz? So if I look at 2 here, and I come over here to 50 kilohertz, which one, blue? So right here at 49.9 kilohertz, because that's about as good as I can get, we can see that our magnitude is indeed -9 dB, which is what we would expect. So we have shifted our frequency spectrum, or our frequency response of our fourth order filter, from 159 millihertz all the way out to 50 kilohertz while maintaining all of the other characteristics. Okay. So I wanted to talk to you guys and introduce this concept of scaling and all of that kind of stuff, because that is how we are going to, that's what we are going to use to design any possible filter, okay? So the big table that I gave you guys, all 5 pages and change of it, I have a digital copy up here. And so I just want to, before we get into the nitty gritty here, I just want to kind of go over what you have in front of you, okay? So the first table is a Butterworth low pass filter table where our cutoff frequency is 1 radian per second and our source and load resistance are matched. So literally, the values of my circuit that I just gave you guys came from right here. Okay, that's all it was. Now, this table has anything up to a 10th order filter, which would be negative 200 dB per decade roll off if we were so inclined. The issue with why we don't use just really high order Butterworth filters for everything is because it's a lot of components, which means it's expensive to implement both from a cost perspective and a space perspective. Yes, Caden.
That's the only reason why you want higher level.
Yeah, absolutely. So we're trying to get to closer and closer to a brick wall response. So let me, before we go into this, I guess maybe I should very basically review. Oh, that's why it's doing it. I am actually on the right thing. So let's just say we were interested in a low pass filter, okay? And this is just a quick aside / review thing, right? So my frequency response for a low pass filter, where this is in decibels. So let's just call this the magnitude of h of j omega in decibels. And here is omega, okay? Let's say, just for shits and giggles, that this is 10 to the 0, or omega is equal to 1. So that this would be 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, so on and so forth. Actually, I'm not even going to need that much space on that side. I need to make sure that the space on this side is legit. So let's put this at 0 dB, minus 20, minus 40, minus 60, and so on and so forth. Okay. So like realistically, I'll do ideal in red. So in the ideal case, we would want to pass all low frequency signals. And then as soon as we hit our cutoff frequency, which in this case is an angular frequency of 1 radian per second, we would want to attenuate literally everything else, meaning that we want a slope of negative infinity per decade. That is an ideal filter. That will never be achieved, okay? For a first order filter, we would have something like this, where we have a roll off of negative 20 decibels per decade, right? So this is n is equal to 1, and I'm going to put negative 20 dB per decade of slope here. For a second order filter, it would roll off like this for our hand Bode plot. For a third order filter, it would roll off like this. And for a fourth order filter, it would roll off like this, so on and so forth. So the higher order filter we have, the more closely it approximates that ideal behavior. Okay. But it would take a really, really high order for us to actually get to, effectively right after our cutoff frequency, our signal is fully attenuated, however we choose to define that. Toby. So not really. So there's because we so let me rephrase that. For the Butterworth topology and the Chebyshev and the Besnell filters and all of that kind of stuff, you were not losing any attenuation other than the ratio of the resistances to the source resistance to the load resistance. That's the only attenuation kind of thing that we worry about there. Everything else is energy storage elements. So as long as we're not putting in a ton of power in so that we have large losses, and we should be fine. Okay. So anyway, so basics of ideal filter versus higher order filter and what order does and all of that kind of good stuff. Similar for high pass, band stop, generally behaves like this, right? The higher order we have, the steeper the roll off or the steeper the transition from the pass band into the stop band. So anyway, going back to the table, okay? So we've got this table for low pass filters, Butterworth low pass filters specifically, where omega C is 1 radian per second, RS is equal to RL. Well, there's actually two different ways that we can implement this circuit. The one we just did, nope, I don't know what that is, but I don't want it, like this, or we could slightly change it. And instead of having a capacitor as our first energy storage element or a capacitor in shunt or across, we could have an inductance in series. Either one of these topologies gives us a low pass Butterworth filter. Okay. So if we want the capacitor in shunt, we read the table going from top to bottom. If we want to start with an inductor in series, we read the table going from bottom to top. So the first value, so if we wanted a fourth order Butterworth filter where our inductor is in series, then the 0.765 would be the value of this inductor. This 1.848 would be this capacitor. Then we'd have 1.848 for this inductor, and then 0.765 farads for this capacitor. So we can use the table either looking down when we want capacitor in parallel or looking up when we want inductor in series, okay? So all of this table right here is purely for Butterworth filters where RS and RL are equal to each other. And then we can use the scaling relationships to change omega C and change both RS and RL. Okay. The second table that I gave you guys is what we would use to design a Butterworth low pass filter when RS is not equal to RL. So we have a different ratio, and that's why it's divided by these ratios. So if RS over RL is 1.111 or 10 over 9 effectively, we would use these guys. If RS over RL is 2, we would use these guys, right? So looking at the table going down means that RS is always greater than RL. And if RS is much, much greater than RL, we use this guy down here. Hmm? Much greater than 10, yes. So if our source resistance is like 10 kilo ohms and our load resistance is like 5 ohms, use this guy. Now, what happens if our load resistance is greater than our source resistance? None of those things are caught here. Well, that's actually reading the table in this direction. So when RS is greater than RL, we read it down. When RL is greater than RS, we read it up. Okay. And if I scroll down to the bottom here, you'll see the extra thing here telling us now, looking at it going up, these ratio is RL to RS. So realistically, we just want to use the entry on the table that is closest to what the situation we actually have is, because we can't do this for literally every possible combination. The table would be too large. Once again, two different ways of implementing this particular type of filter, right? So capacitance in shunt or inductance in series. Yes. Nope. So those are just the two different ways to implement it. So let's work an example, and this will better explain it. I'm getting slightly ahead of myself, but it'll be okay. So let's say how much time? Oh, okay. So let's say, just for the sake of argument, let me see, 1, 2, 3, 4, 5, 6. That we want to design a sixth order low pass Butterworth filter for RS over RL is equal to 0.1. And let me have to go back to the previous example so I can figure out what the resonant frequency is, because I'm getting ahead of myself. Our corner frequency FC is, once again, let's do 50 megahertz. Okay. So these are our criterion. And then on, I guess, next Monday, we'll work the first part of this example problem to explain why we're doing a sixth order Butterworth filter. And it's just, yeah, we'll get to it. It's not a big deal. All right, so sixth order low pass Butterworth filter for RS over RL is equal to 0.1. So we're looking for sixth order. So I'm going to come down to N is equal to 6. And notice that I literally don't have an option for RS over RL is 0.1. But I do have an option for RL over RS is equal to 10. So effectively, I'm going to design using these criterion. And David, I think I may have said a mistake here. I believe we are going to use this bottom representation for RL greater than RS. Okay. So this is our starting circuit. And now we need to just figure out what our scaling values and all of that kind of good stuff are, right? So okay. All right, so our general circuit would be something like this. Here's our input signal. I'm just going to leave it like that. Here's our RS. Here's L1. C1. L2. C2. L3. C3. And then RL. So let's put some values in here for all of the inductances and capacitances and all of that kind of good stuff. Okay. So I'm just pulling those directly from my table. So I should have 0.026 Henrys for my first thing. And then I think this is also going to be 0.026 because they're usually symmetrical. Nope, I was totally wrong. It's not symmetrical because the RS and RL aren't equal. My apologies. Let me erase that. Remembering things incorrectly, my apologies. All right, 7.705. Zero 0.122. So that I don't have to keep going back and forth, I'm actually just going to use the damn physical table in front of me. $15.786, 0.179, and 15.738 farads. Yes.
First value is C4, but it's your elbow value.
Because we're reading it going from bottom to top. Because, so let me go, yep. So because RL is greater, our RL to RS ratio is 10. This is L1. This is, and so on and so forth. Did I label those oddly? Yeah, of course I did. Let me just make it match the table exactly. 3, 4, 5, 6, just so that it matches the table. Sorry about that. There's just alternating between inductance and capacitance. Okay, so now we aren't given anything specifically about what the values of RS and RL are, other than their ratio is 10 to 1. So we might just put 100 ohms here and 10 ohms here and call it a day. That satisfies it. So there we go. Okay. So now we need to figure out our scaling stuff, right? So sorry, I have in here my notes that Km is equal to 500, but I also have no explanation for why that is. We'll figure it out. All right, so I am concerned this is not going to work, but we'll figure it out. So we'll learn together, just because I don't remember how the magnitude scaling works when these values aren't the same. So I'm just going to base it on RS for right now, and we'll find out whether or not I'm wrong in a couple of minutes. Okay. So this should be RS over 1 ohm, because our original table and all of that kind of stuff would have been done for a 1 ohm resistance. So I think our magnitude scaling factor Km should be 10. Okay. Like I said, we'll sort that out in a moment. For our frequency scaling factor, this part is much easier. So our target resonant frequency or cutoff frequency is 50 megahertz. So that's going to be 2 pi times 50 times 10 to the 6th over 1, which is just pi times 10 to the 8. Okay. So using this, L1 prime, how did I get that 500? Sorry, should be 10 over pi times 10 to the 8 times 0.026 henries. I'll grab a calculator real quick. So 0.026 divided by pi times 10 to the 7 is 8.276 times 10 to the minus 10 henries. Or 827.606 pico henries. C2 prime. So that is going to be, that should be 7.705 farads divided by Km times Kf. So that's just going to be pi times 10 to the 9. Bless you. So that comes out to be 2.452 nanofarads. L2 prime would be 0.122. So that's just 10 times pi times 10 to the 8 over 0.122 henries. And over 0.122 divided by pi times 10 to the 7. .883 nano Henry. Dang it, that's supposed to be a 3 there. My apologies. C4. I'm just coming back up here, so that's 15.786. Farads over pi times 10 to the 9. Gives me 5.025 nanofarads. L5 would be 0.179 henries over pi times 10 to the 7.
That means the eighth, there is, okay.
So it should be 10 over 10 to the eighth, which is the same thing as 10 to the 1 over 10 to the seventh. So I'm just cutting out the middleman of taking this guy out and lowering that guy by 1. So 5.698 nano Henry. And then let me do just C6 over here. And let's see, that's going to be 15.738 over pi times 10 to the 9. Which is 5.0095. So let's put 5.010 nano barads. All right. So 50-50 shot of this thing being askew, just because I'm not 100% sure on that scaling factor of whether it should be 10 or 100, because I'm basing it off of RS and I don't remember if it's supposed to be off of RS or RL. Caden, how may I help you? So 100 is 10 to the 2 times 10 to the 6 is 10 to the 8. Okay, so let's build this thing in LT Spice and see how much of a jackass I'm being today. So I'm going to do this the laziest way possible. And by that, I mean I am just going to take one of my original circuits. Let's delete this guy down here. Let's zoom in so that we can see what the hell's going on. Oh, dang it. Well, I'd have to rebuild the whole thing because I'm using the inductor thing. Dang. All right. So let's see. So I've got a voltage source. I wish this thing would stop. Oh my God. Escape. Let's just move that down to the bottom. Resistance. So I put this as a 10 ohm resistor, right? So just for what it's worth, we designed, or we said in the design criterion that the ratio of RS over RL is 0.1. So I'm just looking for any resistors where that's true. So because I put a 100 ohm resistor as RL, RS had to be 10 in order to make that ratio correct. Sure. Absolutely. Let's see here. Then I have an inductance. And then I'm going to put another one here and another one here. Capacitance here, here, here. A resistor over here. And let's just wire this stuff up. So let's see what we got here. Scroll down. So 827.606 pico. I'm just going to do 0.823 nano. C1, or excuse me, C2, 2.452 nano. .883 nano. .025 nano. This dumb thing out of the way, 5.698 nano. And I think this one was 5.010 nano. This was 100. Simulate it. AC. Decade. What's the rest? This is supposed to be at 50 megahertz. Okay, so let's just start at 1 kilohertz. Oh, that's not the right thing. Oh, I didn't label my voltage. Thank you. Nope, that's the wrong thing. Rerun it. No errors this time. Good Lord. So it seems like my assumption that that was supposed to have been based on RS was very wrong, because that actually looks a lot like how a Chebyshev filter behaves. So tell you what I'll do. We've only got 5 minutes left of class. I will work this out, remove my head from my ass over the weekends, and we'll revisit this correctly on Monday. Sorry about that. Yeah, so it's literally just the resistor scaling factor is incorrect. So I'd be willing. So I based my scaling factor. Let me just talk about it. So I based my scaling factor on RS as compared to 1 ohm. And it looks like I might have should have done it to RL, but that would only. Yeah, so like that would make this guy. My inductor is 10 times larger and my capacitor is 10 times smaller. Let me just see. Yep, there we go. I should have just based it on RL. So just for what it's worth, if you guys are still paying attention, boom, fixed. That literally just makes all the inductors 10 times larger, all the capacitors 10 times smaller, and we get the exact response we want. So anyway, sorry for not having that in my notes. I have no idea where the hell I got the number 500 that I have written down. It literally makes no sense whatsoever, but I will revisit this with better explanations on Monday. But anyway, easy enough fix. Sorry for being a confusing asshole more than usual.